After hearing many talks and seeing people around, I feel that although I've been in the right generation, so to say, I'm one of those few who haven't had the opportunity to have any interaction with AKR and gather some cherishable memories. So I feel a little sad about it and slightly out of place. However, coming to IMS is like homecoming, so that also makes me feel very happy. And for that, I thank the organizers for including me in this. What I'm going to talk about today is something that began when I taught a course on thermodynamics, first time in my life, a couple of years back. And that time, for the students, I gave a paper to read as a reading material to see where thermodynamics comes in the context of black holes. The student did a good job, read it, understood algebraically, it was fine, but that kept me into some hook in my head, some puzzles, which from time to time I keep thinking whether the puzzle is really there or not there. I'm not completely sure of that. So to resolve that, I will just have to work on it and find out what it leads to. So what I'm going to do is to share some of the preliminary thoughts. I don't have any complete results. I have some rough plan of how to go about doing it. So that's what I'm going to share about. So I put this instability in the bracket because it's a question really of having a region where there is both stability as well as instability. And the question is, well, we'll see what it is. I think I will read it here. Looking like that is much harder for me. So already we have had some introductory remarks about black hole thermodynamics. The formal similarity of laws of black hole mechanics and thermodynamics is posed also a challenge that what to do with the temperature. And that was resolved by, of course, discovery of Hawking effect. So that sort of said that, okay, it is possible to interpret the laws of black hole mechanics, especially the stationary black holes. And that is fine because of Hawking effect. It's a quantum effect which is necessary in order to interpret the temperature. Now, but it also suggests possibilities of phases and this thermodynamic instability. For instance, for particular values of, so consider the Kerr-Newman family. So for particular values of the angular momentum by mass square to be given by this peculiar value of square root of 2 root 3 minus 3 and q by m, which is root 3 by 2, the Kerr and Reisner-Nordstrom black holes are thermodynamically unstable. This is something which is well known. The location of this is perfectly fine. Its physical understanding, on the other hand, as well as what it implies, to my mind is at least not very clear, certainly not clear to me. So this is the puzzle that I will try to highlight and share my thoughts on that. While the work of Davis, which is one which gives all these details, 1977, discusses the thermodynamic aspects of Kerr-Newman family. I will restrict to Reisner-Nordstrom just for simplicity. Real interest will be for the Kerr black hole, but that is harder to proceed. I will comment on that in the end. So I will deal with Reisner-Nordstrom. Okay, here is a quick recap. Already some of these things you already heard. I will just give some additional formulae. So typical compact bodies, as seen from far away, have three basic parameters, namely mass, angular momentum, and charge. Stationary black holes have exactly three and no more, but they also have some special sphere with its radius and area given by this r plus is equal to the usual relations that we have, and area is given in terms of r plus square, 4 pi r square, plus j square by m square in case there is a angular momentum, j is non-zero. We also have the relation between these parameters, m, j, q, and area, which is given by the smart relation. All this is completely well known, explicitly calculated and demonstrated from purely looking at GR and black hole solutions. If you consider small variations, which is so-called equilibrium form of the first law, then you also see that these nearby solutions with these parameters, mm prime, jj prime, qq prime, etc., they are related by dm is equal to kappa over 8 pi dA plus omega dj plus phi dq, where kappa is the surface gravity, A of course is the area, r plus is the, omega is the angular velocity at the horizon, at the r plus radius, which I will, like everybody will call the horizon, and the electrostatic potential phi at the same location. they're actually derived in some different fashion, but for conveniently, if you want to quickly just remember a few expressions and calculate what they are, one can simply use this first law and then obtain them as kappa is given by the usual relations from taking partial derivatives. That is just a simple mnemonic. It is not the way it was derived. It was derived first from the solutions, finding out what they are, how to define surface gravity, etc. And they happen to we put all this together, and what you get is the smart relation, and the rest of it follows. But for remembering it quickly, it is easier to just look at this law and then calculate the derivatives. It's a lot more easier. So for that, it's convenient, of course, to use the last relation. I will now restrict to Reissner-Nordström family. So J is equal to 0. This is just for simplicity. So from that previous formula, you can calculate, or no, otherwise look it up in Wald's book, for example. Kappa is given by R plus minus M by R plus square. Electrostatic potential is given by Q by R plus. And 2 M R plus is equal to R plus square plus Q square. And this implies, from these three relations, there are only two independent parameters here, M and Q. So you can eliminate R plus and rewrite things in terms of R plus and M. And what you get is a relation between the charge, the electrostatic potential, and the surface gravity kappa. This relation, of course, is completely independent of thermodynamic interpretation. It just follows from these relations that I give you. This is interpreted as equation of state. Just if you consider van der Waals gas, then you have the PVT, so you at least need those three variables. Pure Schwarzschild is not very useful for this because it doesn't have enough number of variables to look at these features. That's why I've looked at either Kerr or Reissner-Nordström. So here is a plot of the equation of state. This side on the x-axis is the electrostatic potential phi. On the y-axis is the charge q. And this always, looking at this equation, you can see that when you take what is you can plot it very easily, either numerically or just analyze it. You'll see that it has always a maximum at phi is equal to 1 over square root of 3. And at that value, you can find out what are the values of corresponding Q, corresponding M, corresponding R plus, and so on. And you find that the ratio Q star over M star is this root 3 by 2. This ratio, of course, the surface gravity cancels out. This again is still independent of anything to do with thermodynamic interpretation. If I now consider thermodynamic analogy, then of course I can talk about the specific heat, which will correspond to saying that T ddt of entropy. So they are proportional, so I just cancel those factors. All I need is just to getting this relation. So this Q is simply straightforward calculation, just gives this, and this diverges at R plus equal to this denominator equal to 0. And that, of course, just means it's exactly this value R plus, which is 1 by 3K. Okay? So this shows that this is the region where, this is the point at which the specific heat is going to be divergent. This phi going to 0 part will correspond to the Schwarzschild limit, because phi equal to 0 also has Q equal to 0, so that corresponds to Schwarzschild limit, whereas phi equal to 1 also has Q equal to 0, but that corresponds to the extremal black hole limit where both M and Q go to 0. And this is the region where this line divides the two regions. Now, if I look at any particular line here, this line corresponds to constant kappa. So now we'll use the thermodynamic analogy terminology and call it an isotherm. So for constant kappa or constant temperature, if I move along this line, as phi increases, I will see that the mass decreases as well as the radius of the horizon also decreases. So as you go from this line anywhere, you're going to see that the mass decreases and size also decreases. This is just to keep in mind what kind of behavior follows. Analogous regions also exist, as well as spatial ratios also exist for Kerr family. The values are not so universal, not just 1 over root 3 kind of thing. It keeps varying. But nevertheless, those regions do exist. Now, this graph as well as the spatial points exist regardless of I interpret this thermodynamic interpretation or not. All this simply completely classical. Just the relations are there for stationary black holes, and you just calculate and you get this. Dynamically, nothing special happens at these values because Rn family is stable under linear perturbations for all ratios between this. So also for Kerr, where stability of black holes we already was mentioned yesterday. Only with the thermodynamic interpretation, however, The region with phi less than 1 over square root of 3 gets the label of instability. Till then, there is no notion of thermodynamic instability because there is no thermodynamic interpretation. Since the thermodynamic interpretation arises due to quantum effects, so must the thermodynamic instability. So I must blame the instability, this occurrence of this, on quantum effects. Precisely what happens at the spatial ratios is what is the puzzle, and what exactly happens is the question. There are many facets of this. When I started looking at it, there are so many different aspects to this to figure out even exactly what you want and what you don't want. It took quite a bit of time. I'm still not completely through with it, but here are a few of the things that one knows. So to talk about phase transitions, normally if thermodynamic instability is there, one will imagine that system put there will move away from that to some direction. Now I don't know which direction it will move, whether it will go towards left side or right side, I do not know that. That will depend upon further properties. So there is a possibility of phase transitions. What these two phases mean also is not very clear, at least for the family as it is given. So initial attempts at understanding this phase transition was to put the black hole in a box so that you have sort of two systems which are in equilibrium in some sense. If that is the case, so the box is filled with thermal radiation and reanalyzed for thermodynamic stability. Now one is doing conventional thermodynamics by putting the ordinary black hole, in this case Reisner-Nordström, put it in the box, put radiation by hand, and ask the question about use a thermodynamic thing to say where the stability and so on. So Hutt in 1977, just before Davis's paper, carried such an analysis. There are many possibilities that arise. Once your system which is more than just the black hole solution, radiation is added by hand, there are many possibilities, many kind of things can happen as you take various limits and so on. All this can be physically understood by saying that there is an energy distribution, division between what is the black hole mass versus what is the contribution to the radiation. This keep flipping as you go across the thing, and that is what is understood as phase transition. Okay? Physically one can understand it. There is some mechanism which takes place which says that we will either realize one part or the other part as the parameters are varied. This understanding, however, is not directly applicable to our puzzle because our puzzle is not with additional matter or additional system put in. This is purely thermodynamic analysis, with no particular explicit role for quantum effects. Because this is just simply saying that if it's a hot body, I put radiation and then ask the question what happens. So this is, although it's true, it is not directly relevant to the puzzle that I have. Something closer to the quantum effects is work in Monteiro's thesis, a student of Hawking, saying around 2010. It's a nice thesis, very readable, very clearly written, who calculates one loop partition function and correlates the transition ratios, these peculiar values that arise because of a negative mode at a one loop level, one loop corrections. So rough idea is the following, that local thermodynamic stability is characterized in terms of concavity with respect to an intensive parameter like kappa and convexity with respect to Q, an extensive parameter, say for the Helmholtz free energy. Now free energy being related to partition function, one may hope to see instability by computing partition function incorporating quantum fluctuations at one loop. This is what is done. So in the paper what it does is to take the Einstein-Hilbert action and Maxwell action and then fluctuate up and take the background fields to be the given solution, and then take the fluctuations calculated at the quadratic order, you will get determinant. And in case, and look for what are the eigenvalues, what are the modes, when they are positive, when they are negative. And he shows that this happens, you get a negative mode, which will make the partition function, the integral, ill-defined, precisely when you cross this peculiar values of √3/2 for Reisner-Nordström. There are many technical details again here about how to handle conformal mode infinity and so on and so forth. All those are discussed well in that. Again, my point here is to simply correlate that what one expects from reasons for instability being quantum mechanical is seen in the sense that quantum fluctuations that you do for around a classical solution are indicating that this is where the instability should take place.
Fluctuations are gravitational fluctuations?
Yes, there are fluctuations about the gravity as well as Maxwell field.
As well as the Maxwell?
Yeah, for Reisner-Nordström.
And you integrate for both of them?
On the small fluctuations, yes. Okay. Half of it is,
Maxwell,
yeah, Maxwell, yeah. What did I say?
No.
Oh, sorry. Yeah. Half of his thesis again is related to put this thing in higher dimensional theories as well as ADS and so on and so forth. All that part is not relevant for my discussion, so first 100 pages about that is still very good. It's a nicely written thesis.
And he's carrying out these integrals in this black hole pattern.
Yeah. So you fluctuate amount, take a classical solution, fluctuate, leading term will be the standard action that you calculate for. All this is done in after Euclidean continuation, and then calculate the one loop part. Again, there are many subtleties, as I mentioned, what to do with the conformal mode, etc., etc. But the upshot is that the quadratic correction term acquires a negative mode, which renders the partition function ill-defined precisely when the thermodynamic instability sets in, for example, for q less than √3m/2. Well, interesting, this is really a manifestation, verification that the proposal of Euclidean path integral method to calculate relate to thermodynamics. It verifies it, it's consistent. However, there is no explicit mention of Hawking radiation, nor is there any back reaction, because only simply calculating what happens for a given solution, small fluctuation. But it is nice in the sense that at least correlates with the fluctuations to the instability.
Sorry.
Yeah.
So when you say you're confining to paths which are periodic.
Yes. That is why partition function involves the trace. That is why. Partition function involves the trace. That's why the closed paths. Periodic path.
Are you imposing, it's not just you're perturbing about the solution, right? You're additionally assuming something is thermal.
Yeah. So I mentioned that thermodynamic will tell you that you have to calculate the free energy. Free energy is related to partition function. How do I calculate partition function for that? For this gravitating system. So calculating any partition function, I will first write e to the minus beta h trace. If I write a path integral representation of that, what I'm going to get is my t minus t prime will become I times beta. This is done in Hawking and Gibbons' work. So I will write the usual path integral, which is transition amplitude, make this t minus t prime go to I beta, so that will make it into Euclidean part. Then I have to also define my integral over the action, which itself has problem because the solution per se, if I take, has divergences, the curvature singularity. So I have to, the idea is that you think of this as a contour and deform it, etc., etc., and a lot of stuff is there. So after doing that only, you're computing, so because you're calculating partition function, there is a trace involved in that. And trace means you have to look at the paths xx prime transition amplitude, x must be equal to x prime, and integrate over x. So that's where the closed paths are coming from. Yeah. So this is nice to that extent that it relates something with at least fluctuations, if not quantum fluctuations. So we have some information about the Hawking radiation. This all similar work is also available for charged black hole. That is work of Gibbons in Communications in Mathematical Physics. I did not write here because I could not quite say exactly what the conclusion I can get from that. But again, this is something to be seen, what happens when your charged particles, charged radiation, when the charged radiation is comparable to energy radiation and so on and so forth. So there are issues involved in that, which is discussed well, but I have not grasped it to the extent of summarizing it in just 2 lines. So that's why I have taken the slide off. So we have some information about this Hawking radiation for black hole and the regions of stability or instability, the 2 regions that I showed you. One region is stable, other is unstable. We do not quite know the fate of black holes in either regions or at the boundary. So if I happen to create a black hole by some means, put it in left side of the line and right side of the line, what will happen to it? That I do not know. So to explore these possibilities, we need to be able to track the evolution of the black hole, both from formation, because I want to put the black hole in either left region or right region. And since there are quantum effects, there is Hawking effect, there is radiation, it may disappear, may not disappear, as Penta pointed out in some cases, it may not completely disappear, etc. We need to find out what happens there. So obviously, this must include the back reaction because we are not looking at only stationary backgrounds or situation which is dynamical backgrounds, not background, but dynamical spacetimes. And those we have to see how to track it. Now clearly for such a tracking, we cannot quite use the definition of black hole based on global notion of event horizon. Because in order to do that, I must carry out my numerical otherwise integration to the entire space-time and then ask the question, where is the event horizon? Is there a black hole or not? Based on the notion of event horizon, which is global notion. So I cannot do that. I must have some different quasi-local version of definitions, which provide a criterion to say whether black hole has formed or not formed, and also to identify a quantity which is appropriate to talk about whether that's quantum radiation or not. Because again, if I don't go up to infinity, do I really talk about radiation, or do I talk about some flux, or do I measure the flux near the horizon, whatever near the body? I will have to understand what exactly to do, how to decompose that, and identify what is quantum radiation or classical radiation, and whether this happens, it correlates with the formation of quasi-local horizon or not. I must address all these questions. So the former notion of quasi-local horizon is provided by the so-called notion of dynamical horizon, and the latter should be related to expectation value of the stress tensor, and in our case for charged black hole, also the charge current of a quantum field, because I'm looking at Hawking effect as a potential method of quote-unquote stabilizing or destabilizing the black hole. So that such a field should collapse, and should track the evolution of it from collapse all the way to where it takes me. So that is the thing one would like to have. Now, here is a very completely minimal basics for dynamical horizons. The crucial idea of black hole here is the occurrence of trap surfaces. This is what Nobel citation for Penrose's work says, that formation of trap surface or the marginal of that, not event horizon, is something which is taken as a signature of, can be taken as a signature for black hole. Practically, of course, when you're talking about black holes in sky, we don't even know. If you think of them as being in universe is not asymptotically flat, so there is no sky plus, sky minus, and event horizons. So those notions may be nice for proving theorem. They are very useful, of course, but they are not necessarily useful in practical terms. There is alternative characterization in terms of trap surfaces. So that is the idea which is taken to say that when do we say, quote unquote, black hole-like object has formed or not formed? That's a quasi-local definition. So given a closed two-dimensional space-like submanifold, which is a spherical topology, we have two natural congruences of outgoing and incoming null geodesics. Let me denote one of them, represent those by vector fields, standard. L mu, let's say, is outgoing, and N mu, which is ingoing. The surface then is called future trapped if the expansion, that is divergence of these vector fields, of both vector fields, is negative. Then we say it's future trap. There is a definition of future trap, past trap, outer, or so many, again, shades are there. If one of them is 0, one will say that the surface is called marginally trapped, which will be sort of generalization of what will enter in the notion of apparent horizon. A dynamical horizon delta, so getting this idea of, introducing the idea of marginal trapping, first characterizing what you mean by that, and then saying that, can I now find out in my numerical evolution or otherwise, at a certain Cauchy slice, certain time, when I scan it, do I find such trap surfaces or marginally trap surfaces or not? If I find, then I say, okay, I have some candidate black hole. So dynamical horizon now is taken as a three-dimensional submanifold, which is foliated by marginally trapped surface. It is not a null hypersurface. It's foliated by marginally trapped surfaces. So the idea of trapping is there, which is what distinguishes whether you are having something can escape that region 1 to region 2 or not. And this was developed by Ashtekar Badrikrishnan. The Living Review has a detailed discussion of this with lots and lots of results and so on. Results, subtleties, technical definitions, and so on. So I'll just note a few of them, which I need for my argument. So first of all, the area of suitably identified two spheres, these cuts on this dynamical horizon, they are taken to be spherically symmetric, topologically spheres. So their areas can be identified. They increase or decrease depending upon whether the local flux, energy flux is ingoing or outgoing. So if the flux is falling in, there is an equation which will say that the area will increase, or it is going out, the area will decrease. This is analogous to the statement that you throw something at the black hole, the area will increase or not. So this is roughly the incorporation of second law, quote unquote, because it's not a dynamical situation, it's not an equilibrium situation, but that's analogous to that. So that relation exists. If the flux vanishes, either going or incoming or outgoing, then the dynamical horizon goes over to another version called isolated horizon, which is the one which is for which entropy, etc., is calculated. But there is a smooth way of joining what is a dynamical horizon defined the way I just described. that it can transit to an isolated horizon, which is also defined analogously with some slightly different conditions. They can join smoothly. That is useful for stationary limit. Now, for isolated horizons, which is what is closest to the horizons, black hole horizons that we talk about, there are quasi-local definitions of the conventional black hole parameters, namely m, j, q, a, kappa, omega, and phi, and they have the same form of the first law of black hole mechanics. So that holds even for isolated horizons. This is purely classical analysis here. Okay? So first law of black hole mechanics also holds. There are many, many first laws, but you can choose one which corresponds to saying that these isolated horizons, which are also solutions of Einstein's equations with their infinite parameter family of solutions, which will have isolated horizons as their boundaries. For such solutions, I can define this. So for such solutions, I have infinitely many of these first laws. But for among this class of solutions, there are also the known solutions, Kn family, for example. So I can say that I choose this kappa, j, etc. parameters in such a fashion that they match with these solutions which are well known. Once that is done, the first law is fixed. For these also, the Smart-like formula also holds. So whatever we wrote in the beginning, that formula also holds. And therefore, all the thermodynamic relations that we had before, because they depended only on the fact that Smart formula holds and the first law holds, that was sufficient for it, they all carry through exactly as it is. So provided you also have analog of Hawking radiation coming from isolated horizons, then you have the thermodynamic interpretation, and therefore the same things that we had, equations for the same quantities that we had will show up. To my knowledge, there is no explicit calculation of how to do Hawking radiation in isolated horizon case, because I don't know how that happens. Fine, so this is something that one would like to do. Now there is an example which tells you how the tracking can be done, how can be implemented. Again, it is done in the semi-classical evolution of the so-called Cullen-Gidding, Harvey and Strominger model, CGHS model. It's two-dimensional model which contains a metric, a Dilleron field, and n massless scalars. The evolution is obtained by semi-classical equations. That is, you take the classical equations which are there, but the right-hand side, the stress tensor that you will have, will be coming from the scalar fields which are taken as quantum, the quantum mechanical expectation values. So once this is done, this evolution has been carried out. The work is given the references. So Ashtekar, Pretorius, and Ramazanoglu. This is PRL and PRD papers in 2011. The references are in the end. They display the Penrose diagram. Again, I am not drawing the diagram here, but I will write down what are the salient points of that. So some striking points are the following. The space-like dynamical horizon never forms. So what one would have thought of as quote-unquote black hole, it never actually forms. There is singularity exists because you are still doing semi-classical analysis. Although you have back reaction, your background field, in their case, it's only, there are no charges there. So your dilaton field or metric essentially still continues to have singularity, because singularity is not resolved in semi-classical analysis. For that, you need full quantum gravity, if at all. Then the singularity exists, but it is weakened. The technical way of the singularity is whether it is continuous or not. It differs at that technical level. Only time-like generalized dynamical horizon forms. I define the dynamical horizon with saying that this is a surface which is space-like surface which is foliated by marginally trapped spheres. You can generalize the notion to also considering time-like surfaces, and those will again foliated by marginal trap surface. So if those are there, then they are called generalized dynamical horizons. Only those form, and their area keeps shrinking due to Hawking radiation. So there is quantum mechanical radiation, the flux that you calculate for T mu that exists, and the area keeps shrinking. And in that whole process, there is no null infinity. So there is no question of trying to define event horizon. These are qualitatively different from what we would have expected, collapse of a black hole without back reaction. Okay, so back reaction plays an important role in this evolution. It's a fully dynamical situation. It's not entirely.
When you mean null infinity, you are referring to scribe plus?
Scribe plus, yeah. Yeah, that's what I mean. Okay. So now the work in progress. So having gotten this, so first the puzzle is there. In order to gain some understanding of puzzle, you need to consider dynamical situation, how the black hole forms as well as how it evolves and evaporates or doesn't evaporate, whatever happens. So we need the tracking. For that, I need to introduce quasi-local horizon notions. I also need to find out how to calculate the stress energy, tensor T mu as well as J mu, its expectation values, how to choose the quantum state, how to evolve it, etc. Once those things are there, it is possible that I can actually carry out track the evolution and then ask the question, then what happens? Is there something now which says that if I choose my initial condition in this manner, I'm going to fall in the unstable region, somewhere I will come across it, or it will enter there but somehow go away, or it goes into stable mode, stable region, and happens to stay there for longer time and then evaporates. What happens exactly is something that one will not know until one has done the evolution. But what to do for the evolution part is reasonably clear, at least morally clear. So idea now is to use semi-classical equation. One is still not trying to talk about quantizing either the electromagnetic field or the gravitational field. One is not doing that first. At some stage, one will need that because your semi-classical approximation itself can be questioned. It can break down. So at that stage, you have to say, okay, I cannot trust my evolution beyond that point. Fair enough. But I can see how far can I go and then start estimating it where things can go wrong, where the approximations will fail. Yeah. So the scalar field is taken to be quantum field, while the metric and vector fields are classical. The initial quantum state is taken to be coherent state, and different scenarios for collapse can be seen by choosing the different initial conditions. So these are equations themselves are very easy to write down. That is what I have written so far. I've written in spherical coordinates, but it looks like that is not the best way to do it. You should perhaps choose a different set of variables. Suitable choice of two-dimensional coordinates and a gauge for vector potential is necessary. Many other things will come as I go along and start calculating. Since the scalar field satisfies the linear equation, we can, the hope that something can come out is because the equation is linear and one can attempt a mode decomposition, but the modes are not solved once and for all because they are going to depend upon the background metric as well as background, not background, external, not external. It's the degree of freedom which is the metric as well as the mu field. So I have to solve this coupled system of equation to find out what the mode functions are, and they have to be done as evolution proceeds. They are not given once and for all. They have the expansion as usual. Field will be written in terms of linear combinations of this with operators sitting there. And given the operators, you take expectation values for the stress tensor, which will be del mu phi, quadratic in that. We'll have to worry about the divergences and such things. But that is something potentially doable. At least these are the parts which will not throw me out completely. If they're already nonlinear everything, I wouldn't even try because then you are back to usual perturbation theory and normalization. All the machinery will come and then you'll start scratching your head to see what to do. At least first part here is easier. It is little encouraging. In terms of this, identification of formation of any dynamical horizon as well as quantum radiation is to be done. Many steps in this are not clear, as I told you, the technical points which are not completely clear. Of course, I will first attempt to do it at spherically symmetric models and therefore reduce from 4 dimensions to 2 dimensions. I want to include mu because I want to consider the case of Reisner-Nordstrom. But once the spherical symmetry is there, effectively getting 1 plus 1 dimensional field theory. If I were to attempt to do a similar thing for Kerr solution, then I have only stationarity and axisymmetry. That will reduce it to the effective field, which is 2 plus 1 dimensional theory, which is harder. But that is what one would like to know because at least that is more relevant than charged horizon. But as far as seeing what the features are and how they interact, how the evolution and different things evolve together, Reisner-Nordstrom should be good enough. It's a lower 1 plus 1 dimensional theory, and that is something that is at least initially encouraging. Until one gets stuck somewhere badly, then one will have to worry about it. So many things in that steps are not quite clear, and that is work in progress. I don't have hard results to show because I don't have them. But at least there is a possibility, and it's somewhat encouraging that at least some steps are doable. I mean, you don't get stuck at the right first step. Something is doable. Question is, at least to my mind, the puzzle is reasonably well posed. How one may do that is also reasonably clear, but many details have to be filled in. Particularly is a situation, for example, in the classical collapse case, one had the Choptic phenomenon, where we had the criticality when the massless scalar field collapses. So either it forms a black hole or disperses. And you ask the question that if it forms a black hole and I keep changing the initial condition for the collapse, if the mass goes to 0 to go to the dispersal case, how does it scale with the parameter that I will choose? So that is Choptic scaling. Now, that was the case where you had two possibilities for the collapse. Either you form dispersal, that is Minkowski space is formed, or you have a black hole which is formed. And then ask the question at the boundary what happens. There again, a lot of work on that. Here one can ask a similar question that you have this boundary region which is m by q by m equal to root 3 by 2. So I can start approaching, once I know how to tune my initial conditions to select which region I'm going to get the black hole into, if at all. Then I can ask the question, can I now tune it so that I start getting close to it and ask the question what happens there? One possibility is that it will eventually evaporate. It will always remain unstable. But the amount of time it takes can vary. That's one possible thing that can happen. And that will depend upon which region you are passing through. You are passing through the stable region or unstable region. So it may, that is one possibility. But this is really pure speculation, because until one sees how the things move, it's very hard to guess what will happen. So here are some references. The Davis's reference I told you, which sort of started me on this. This is the old paper, 77. I was puzzled why these things were not sort of pursued further, but I see one possibility could be that one doesn't know how to do the dynamical evolution of this thing well. So that could be one reason. Hurt paper I mentioned, this talks about rational Nostrom case. Montero's thesis is very nice, clearly given. Also talks about thermodynamic stability, instability. It's a very well written thing. Half of it is also related to higher dimensional cases with ADS, asymptotical ADS cases and so on. Ashtekar Badrikrishnan's living review gives all the details about the dynamical horizons. There are further details or simpler versions become available later. CGHS model is, I just mentioned because I referred to it. And CGHS evolution, which is being talked about, are these two papers in 2011, which indicate that what you might expect from intuition of stationary black holes and small changes that happen, Hawking radiation go this way, that way, is not necessarily what will happen if you try to use the back reaction included in that. It can feed itself more and things can change. So that is what I have to say. Thank you. Yeah,
Question?
few questions I can try. Yeah, sure.
Thank you. Very nice talk, Ghanashyam. The first part of your talk dealt with the Euclidean Gibbons-Hawking formalism in some sense. Well, the stability analysis,
Yeah.
the only comment I have there is that there is also a new version where you do a Lorentzian path integral. I mean, that is done for quantum cosmology by Neil Turok and Jean-Luc Leder and others.
Okay.
And they have different saddle points compared to the Euclidean analysis. And there is this argument that in quantum cosmology, for instance,
Yeah.
the Hartle-Hawking boundary condition leads to an unstable universe. So I was wondering whether your stability analysis, well, it's still very difficult to do it for a black hole, so your case would be still hard to do a Lorentzian analysis, but then the saddle points may be different and your stability results may be different.
Well, if I'm looking at entirely quantum mechanical treatment, full quantum mechanical treatment, not small changes and small linearization.
No, it's a perturbation,
Hold on.
perturbation approach.
Yeah, if I'm going to do that, then of course I should go to the Minkowski and Lorentzian signature path integral, because I'm looking at transition amplitudes. Here I'm talking about thermodynamic stability or instability. I'm already talking about thermodynamics, which means I'm calculating partition function, which means I have to go to Euclidean thing, because that's what partition function is defined as. Path integral representation is just a representation of calculating a certain quantity. E to the minus beta h trace is simply given by either summation over eigenstates or write this path integral for that. And that path integral will contain the action, which is Euclidean action. Okay. So for analysis of thermodynamic instability, to my mind, that is sufficient. Saddle point is not, I'm not calculating saddle point from writing the full action and looking at what is the saddle point. I'm choosing a background solution which is given to me, namely whose stability I'm
Presumably
looking
that
at.
is the saddle point, right? I mean, otherwise...
I agree. I'm not discovering whether that remains saddle point or not. That's a different question. I'm saying if this is a saddle point, then do I have fluctuations which will tell me this is instability, thermodynamic instability will straighten at these values or not? So the question asked is a bit different. But I agree that in general there could be other saddle points. Sure enough, I don't have answer to that. I mean, not
And the stability analysis would be somewhat different. That's
a different kind of stability. It's not stability of the given system.
Yeah, I mean, it's a question of whether thermodynamically stable also means gravitationally stable. This was a question that Wald and others also looked at, and I'm not completely sure about the answer. Wald tried to say that thermodynamic stability and dynamical stability should go hand in hand. That would be the guess, but then is that always the case, right?
I think, yeah, go ahead.
I can just make a comment. So Wald and Holland's, what they showed is for non-compact horizons, not for compact. So his talk is all about compact.
Okay, I guess there could be a difference.
No, also, in fact, this thesis I mentioned, he also talks about dynamical stability and instability and thermodynamic stability and instability.
I've read Montero's thesis.
One is referring to really starting with initial data, you perceive the initial data, do I still remain the new solution which is close enough to that, which is not linearization stability. That's yet another notion that one talks about. Thermodynamic stability will come by, I mean, if you want to write equation, I mean, Sventa already mentioned stochastic right-hand side. So one can do something like that, but that is take equations but change the source, classical source to be a stochastic source, and then ask the similar questions. That's another approach. There, in fact, there is whole living review on stochastic gravity, which has all kinds of things. I mean, I've been scanning through mainstream to figure out where do I finally latch on to, because what I want to understand is that part. So how I go about is one particular method. Yeah, you have some comment.
Yeah,
please.
I have one precise question, one vague question.
Okay.
So the precise question is about this comment you made: no null infinity.
Yeah.
In the CGHS numerical symmetry.
That's in their paper, yeah.
What do you mean, like no complete null infinity? Is that what you mean?
I suppose so, because Rusticker always makes a point about null infinity. If it is not complete, event horizon definition will not make sense. So,
okay. And
so presumably that, but since the work is numerical, one will have to ask questions about what exactly is meant by that. So okay. I don't, some of the details I don't know. I mean, they are given many details in the calculation, the longer paper, how it is done. But some things are still not clear. I asked Abhay once, how do you track that when you say in the paper that Hawking radiation starts in earnest? What does that mean? So what do you call it? So it's like expectation value of Q min is calculated, and that's the only thing which is there. You can't run off to infinity say whether that's truly radiation in the sense of 1 hour or fall off or not. That kind of thing you cannot use.
Okay. And the vague question is, so in this thesis, Monteiro, so they compute the Euclidean one-loop determinant.
Yeah.
Can it be computed in the Lorentzian signature, and can it be compared?
I don't know. That is question is similar to what
related to. But there are papers which people talk about black hole determinant and things like those. So what is the relation?
I don't know. But as I said, I don't know why would one calculate that. For what purpose? What is the central quantity you are interested in calculating? I can calculate path integral and ask the question whether it can be done in this way, that way, etc., etc. But what is the quantity that I'm interested in calculating? If I'm looking for thermodynamic stability, not saying whether my quantum theory admits such and such solution, which is an extremum or saddle point of whatever action path integral that I've written, that's a different question. There you are talking about transition amplitudes. Here I'm talking about partition function. There are two different quantities. They all look path integral because you write the integral in d5, but that begins and ends there. There is a trace involved in that.
Maybe it can provide some technique.
Yeah, I think.
So I think what you're saying is that if you're computing Euclidean path integral, because you want to compute trace e to the minus beta h.
And I'm looking close paths here.
Yes. Yeah. Then clearly you'll wonder what a Lorentzian saddle point will do. But I just learned just before I came here that people have been calculating, for example, if you take a particle of, let's say, at 0 energy and leave it from the horizon, how much time it will take to reach the singularity? That's a Lorentzian question.
Yes.
Now, it so turns out, I mean, this one doesn't understand, that the Euclidean path, the Euclidean calculation also gives the same result. So the reconciliation might be that the Euclidean path integral may also have a Lorentzian saddle point, in a sense that one should look at path integrals in complex geometry. And that's a possibility only. I mean, that's all I can say.
One thing could be that since the path integral also contains the e to the minus action part, the integrand, that action itself is taken as a contour integral. So you avoid the curvature singularity and so on. Now there if you make Lorentzian deformation, whether that aids the calculation or not will change, I agree.
Yeah. So
But
also
maybe that is something which can give it, but what do you do with the trace? Either I keep the trace or not keep the trace. That depends on what I want to calculate.
The Euclidean theory doesn't have a horizon nor a singularity.
No. That's because you avoided it by doing the continuation.
Yeah.
That's true. Yeah. We did it for that reason.
Yeah.
I agree. Sure.
Right.
Yeah. I agree. But you are taking trace, and that's partition function. Without that extra integral, it's not a partition function. You call it partition function, but that's not correct.
Anyone else? Okay, so I guess let us thank Shyam for raising a question.
Okay.